Welcome to Fourier Cosine series. So let's consider a function f defined on the closed interval 0L. We can extend f doing an even extension. So we can extend f to be an even function on the interval negative L to L, simply by setting f of x to be equal to f of negative x for negative L less than or equal to x less than 0. Right, so this creates the even extension. Then we have an even function. And the Fourier series is a cosine series. I need to give myself just a little more space. Right, so the Fourier series is a cosine series, right? We know what the even function Fourier series look like. It's of the form f of x is equal to a naught plus the sum from n equals 1 to infinity, a sub n cosine of n pi over Lx, where a naught is 1 over L times the definite interval from 0 to L of f of x dx, and a sub n is 2 over L times the definite interval from 0 to L of f of x cosine of n pi over Lx dx. So just note the only integrals we are doing are on the original domain of f. So note the integrals are over the original domain of f. And so we really are just creating a Fourier series based off a function divided from 0 to L. And we call this the Fourier cosine series. So this is referred to the Fourier cosine series. On 0L. So let's go ahead and just do an example. So if we want to find the Fourier cosine series for f on 0,6, where f of x is 1, from 0 to 3, I swapped my x and 3 there. All right, f of x is 1 for 0 less than or equal to x less than 3, and 0 from 3 to 6. Then we can go ahead and set. We know that we are dealing with a Fourier cosine series. So we have f of x is equal to a naught plus the sum from n equals 1 to infinity of a sub n times cosine of n pi over Lx, except here our L is 6. So we are looking at cosine n pi over 6x. Our A naught is 1 over L. So in this case, 1 over 6 times the definite integral from 0 to L. So definite integral from 0 to 6 of f of x dx. We can go ahead and split this. This becomes 1/6 times the integral from 0 to 3 of 1 dx plus 1/6 times the definite integral from 0 to 3 of 0 dx. So we are just looking at 1/6 times x evaluated at 0 and 3. The rest is 0. So this just becomes 1/6 times 3 minus 0, better known as 1/2. So we have that our A naught is 1/2. Finding our A sub n's, we do 2 over L, so 2 over 6 times the definite integral from 0 to 6 of f of x times cosine n pi over 6x dx. Once again, we split this integral from 0 to 3, f of x is 1. So this becomes 1/3 times the definite integral from 0 to 3 of cosine n pi over 6x dx plus 1/3 times the definite integral from 0 to 3, from 3 to 6. So 1/3 times the definite integral from 3 to 6. Here f is equal to 0, so we're just taking the definite integral of 0 dx. This becomes 1/3 times that cosine of n pi over 6. When we integrate that, becomes 6 over n pi times sine of n pi over 6x. We are again evaluating at 0 and 3. So we are looking at 2 over n pi times sine of n pi over 2 minus 2 over n pi times sine of 0. Sine of 0, of course, goes to 0. Sine of n pi over 2 is a little more complicated. So we are looking at, if we think of our unit circle, over here at 0 radians, that's equivalent also to any 2 pi. So we're essentially looking at 4k times pi over 2. There we have sine as 0. So we're looking at sine of 4k pi over 2 is equal to 0. Our next, working our way at the equivalent of pi over 2, this would be 4k plus 1 times pi over 2, or we can view it as, we'll do 4k plus 1 times pi over 2. This here, we are looking at sine of 4k plus 1 times pi over 2 has sine equal to 1. And at sine of 4k plus 2 times pi over 2, we're back to 0. And then at sine of 4k plus 1, sorry, 4k plus 3, or we can do it as 4k minus 1 pi over 2. We are looking at -1. So again, this is a little more complicated when we introduce those n pi over 2s. We have to pay a bit more attention to exactly what's going on. So in this case, essentially for n even, we have sine n pi over 2 is 0. For n odd, we get either 1 or -1. Right? So what we wind up getting is that this is equal to 0 for n even. So our a sub n is 0 for n even. For n odd, I'm going to call it 2k minus 1 for n odd. We will get either a -1 or a +1, and then multiplying 2 over n pi. So we have a -1 to the something times 2 over n pi. And here is the trick, figuring if we should have a positive or a negative involved. So if k were equal to 1, that would mean n is 1, and we would be looking at just pi over 2. That's the positive case. So it turns out we'll actually need to do -1 to the k plus 1 so that we match. You can also just leave it in the format I used with 4k minus 1 and 4k plus 1. That's fine as well. But this is a shorthand notation. So essentially what we get is that we have that our f of x, our Fourier series, is equal to a naught was 1/2. And we have plus, we'll go the sum from n equals 1 to infinity. Or we can do sum from k equals 1 to infinity is maybe easier. The sum from k equals 1 to infinity of -1 to the k plus 1 times 2 over n is 2k minus 1. So 2 over 2k minus 1 times pi. And then times, we're doing a cosine series, so times cosine of 2k minus 1 times pi over L, which is 6, and then x. So this is how we can go about finding a Fourier cosine series. Again, our original f was only defined on 0 to 6. This is the Fourier series where essentially we take the even extension, just folding over the y-axis, and then take the Fourier series for that function defined from -6 to 6. But because our even functions, the formulas for Fourier series, only depend on the bit from 0 to L, we don't even need to bother with actually writing out the even extension to find the Fourier cosine series. So this is how we find our Fourier cosine series. In the next video, we will take a look at Fourier sine series.